one way to improve the oxidation resistance of nickel is to alloy it with chromium or aluminum or a combination of both. So there are several ways to alloy metal foams. One was pack cementation, casting replication, air plasma spraying, vapor deposition, and slurry cementation. We chose to use slurry cementation because it's simple, fast, and it provides the desired type of coating for our foam. And now Mike will elaborate more on our experiment works.
So after a lot of conversation on about the requirement for this project and the properties of material, we want to come up to the objective of the experiment. We see the diffusion of chromium to nickel form matrix to form nickel-based alloy, and we have to improve the oxidation resistance of the nickel-based alloy form at high temperatures. And based on our literature review, the composition of our nickel-based alloy form should be 88% of nickel and 28% of chromium. First of all, let me talk about this talk a little bit about slurry deposition method. This method consists of two big steps. The first step is coating a layer of metal powder on the surface of the substrate. The second step is using heat treatment to get the desired composition at the strip. You can see this is the metallic powder on the substrate, and after heat treatment, we have the diffusion layer in the substrate. With the knowledge of the slurry deposition technique in mind, we start to make our first slurry at the initial start for the experiment. First of all, the slurry combine three components. First is with the brass gel binder, which is the binder of all components, and the ammonia chloride, which is the activators, and metallic powder, which we use in this experiment in chromium. The contribution of those components can be broken down into 35 to 65 weight percent of metal powders, 1 to 25 weight percent of activator, and 30 to 65 weight percent of binder. The final product is a gel-like slurry, which should look like this. So after making our slurry, we have to make our nickel sample for the experiment. There are two types of samples used in this experiment, with the nickel strips and nickel foams. The reason we use nickel strip in this experiment because it's cheaper than nickel foam, and we can use it to adjust our slurry composition to have the appropriate viscosity for our coating process, which is dipping our sample like this into the slurry like this, and we don't want it too much viscous or too much runny, and we're gonna let it dry for 2 hours. Next, in preparation for the heat treatment process, a tube furnace is set up in our lab room. This tube furnace consists of 3 big parts. The first part is the heating component, which is the green thing, and the silicon tube right here, which is we're gonna put the sample inside of silicon tube, and 2 end caps of the silicon tube, so that we can control our heating environment in it. So after setting up our tube furnace, we advance to the first step of heat treatment, which is burn up the binder, activate our activator at temperatures 950 degrees into hour with argon in normal flow rates. The diffusivity of chromium into nickel will determine the time of diffusion and at different temperatures. Based on the Arrhenius equations on infinite plates, we set up a table at different temperatures and given us a different type of diffusion, which is shown right here. So with based on those calculations, we proceed to second heat treatment with making chromium diffuse into nickel plate at temperatures 1573 Kelvin on 28 hours. This will make chromium diffuse to a depth of 275 micron, which is the average depth of our strut for the core. So after the second heat treatment, sample will be left in air for different living. Sample will be left in air at 1,000 Celsius degrees for different test circles to work with the oxidation test. We will measure the mass gain due to the oxidation, and SEM is used to observe the cross-section of the material to find the thickness of the oxide formation and its diffusion depth. Also, EDS is used to determine the new chemical composition of the sample. So far in our semester, the result we have is the nickel stripe with nickel with the layer of chromium coated on it, and this is the side view of our nickel stripe with chromium on it. That's the good news. The bad news is during our experiment we have a lot of issues. The first issue comes with slurry composition. Our first choice of wire is PVA, which does not mix well with chromium powder and our activator. When we get the commercial gel, we try different composition, and our first composition come out is too fluid, which means it's running and it's running off over the nickel plate, so there's no slurry strap on it. The second issues we have a cost and time. With the brass spider gel, take 2 weeks and $200 to be delivered to our lab room. And the big furnace, the red one, for our second heat treatment is broken, so it's in time to fix. And the third thing is the tube furnace fitting on the silicon tube. It doesn't fit with the end cap of the silicon tube, so we have to order a new one. That's what we have in the last semester. So we come up with a work schedule for the next semester. Would be SEM EDS analysis, which we schedule it on tomorrow, and adjusting the slurry composition to make it better, and apply that slurry into nickel form, and also doing the oxidation test on nickel form. So that's the end of our presentation. We welcome all questions and comments.
So did you guys actually carry out the oxidation test, or is it a plan?
Not yet.
Not yet? Okay.
Because the furnace is broken.
Oh.
Yes.
I was a little confused. You said you had silicon tubes in the furnace. Did you mean silicate tubes? Or?
Yeah, that should be silicon carbide, I think.
Silicon carbide? Silicon oxide?
Yeah. Because that's what the professor gave it to us. I think it's silicon, but then just concentrate on making the furnace work. So.
These predicted times for the diffusion heat treatment, how confident are you in those times and temperatures?
come out in 28 hours. But for the foam, we have to use a different equation for that. Let's say finite rate. It's gonna take a lot of calculation for that. But for the first one, I'm pretty confident because we take on the reference on the library and we do it like a couple times. And it's also studying all the sorts of literature review. That's the diffusivity of that. Gonna go at one point, I think in 28 hours for the second entry. Okay.
Yes.
Do you think the chromium particle size has any effect on the diffusion?
Yes, it does. And of course it affects on the first slurry we make with PVA. The particle size too big, 44 micron. So it's formed like two separate phases on our slurry. That's why we have to order the beta gel wider thing. And the bigger the particle size, the slower the diffusion process. So I think the chromium particle size should be around less than 20 microns maybe first. Yes.
Yes, I want to ask you, did you mean infinite source diffusion or infinite plate, or do you mean semi-infinite?
We use infinite blade for the blade thing and semi-infinite for the foam core.
Right, but I mean, you've got stuff on top which you want to diffuse down, so I think it's semi-infinite, right? In the sense it goes from 0 to minus infinity, right?
Yes.
Yeah.
I put it in, going up like this.
Up or down doesn't matter which,
Yeah.
but it's only half of the half of the. The other thing I was going to ask you is this a limited source diffusion or constant source diffusion problem?
I think, based on my knowledge, it should be constant diffusion.
So you've got continuous supply of material?
Yeah.
It's not as if it's a plating and then you take the plating and you
the plate.
diffuse. Because in plating you have an exponential dependence for the diffusion coefficient and you have an error function for a limited source diffusion.
Because the sorts of chromium plate on the nickel thread. So we calculated it should be have in continuous supply by the thickness of that layer is around 200 micron.
But I mean, that's it. That's all you've got. You've got the stuff that's on top. You don't have it continuously coming
No,
in.
that's
So that's limited source. It's
We
called limited.
don't have it
Yeah.
continuous coming in.
Limited source. So it's
Oh.
usually exponential, I think. Yeah, for long times it goes exponential. Right? Thank you.
Thank you. We need to move on.